NTU, Pisen Chen of NTU and LeCosPA, Zhihong Che of NTU, and Guoqin Liu of Tanggang University. The speaker, Chris Gauthier, is currently a Planck member and also a fellow of NTU LeCosPA. He got his PhD from University of Michigan Ann Arbor in 2010. Then he went to Paris 7 for a term of postdoc, and then he came to NTU as a LeCosPA fellow. Now let's welcome Chris.
Thank you very much, Professor Chen, for that. How am I? Can people in the back hear me? Thumbs up? Good. All right, so as he said, I've been a member of Planck. I've been involved for about over 2.5 years now. Not as long as some, but long enough. And this talk is the universe according to Planck, where we are and where we go from here. So, first I should just give some background about basic cosmology, since everybody here comes from a diverse number of backgrounds. So, according to our current understanding, the entire universe began in a Big Bang, so to speak. A very small, hot, and dense seed that then expanded into the large, cold, and sparse universe that we see today. Now, because of this Big Bang, the entire universe is filled with an ambient microwave radiation, which is called the cosmic microwave background, or, as you're going to hear quite a lot from me, the CMB. By observing the CMB, we are directly seeing the universe as it once was almost 14 billion years ago. So, first some historical perspective on CMB observations. The existence of the CMB was actually first predicted before it was discovered by George Gamow, Ralph Alpher, and Robert Herman in the 1940s as a consequence, a direct consequence of the Big Bang model. And in 1964, this CMB radiation was discovered accidentally by Penzas and Wilson in 1978. They were awarded the Nobel Prize in Physics, accidentally. At that time, though, the temperature of the CMB was observed to be incredibly isotropic. And what I mean by isotropic, because you'll be also hearing that word a lot from me, is that if I look in any direction in the sky and I measure the temperature of the CMB, I find that it is the same in all directions. So at that time, this is what our picture of the CMB anisotropy was, which is to say 0. In the middle here, you'll notice a white region. That's our own Milky Way galaxy that unfortunately does block some of the CMB from our view. So, now I said that it was isotropic, but that's not entirely right. In 1989, a dedicated space telescope was designed to study the CMB, called the Cosmic Background Explorer, or COBE. It was launched by NASA, and it found that the average temperature was about 2.73 Kelvin, so very cold. They also found that despite the incredible level of uniformity, there is actually slight temperature variations, about 1 part in 100,000 across the sky. To put that into perspective, it's like measuring a difference of 1 millimeter in the height of the Taipei 101. So they were able to measure that distance from space. This discovery was one of the reasons that John Mather and George Smoot were awarded the 2006 Nobel Prize in Physics. But we can go further. These observations were followed up by NASA's second generation CMB observatory, called the Wilkinson Microwave Anisotropy Probe, or WMAP, which was launched in 2001. And this followed up on COBE's original measurement of the anisotropy, but it did so to a much greater degree of resolution and accuracy. And the map that they generated of the CMB was this. So blue regions here would correspond to colder regions of the CMB. Red and yellow would correspond to hotter regions. This map, of course, is the average temperature has been subtracted out, because the average is just so much greater than the original. But they were able to measure this, as I said, with a very high degree of accuracy. And because of that, they can now use the CMB to directly determine some of the critical parameters of our standard model of cosmology. And now we come to Planck, which is the third generation. Its namesake is Maxwell Planck, a German physicist who first discovered black body radiation, or is considered the father of quantum mechanics. Of course, you all know that, actually. Sorry. Planck is the third generation. It was launched by the European Space Agency this time, and it was launched in May 2009. It was put in orbit around the L2 Lagrange point, and this is critical because at that point the Earth blocks out a lot of the heat from the sun, and in order for the Planck satellite to work, the instrumentation needs to be very cold. And at this point, it's rotating roughly 1 revolution per minute on its axis, scanning the sky, and it orbits with the Earth. So in about a 6-month period, it is mapped out, it has made 1 full scan of the sky. Planck has made 5 scans of the sky, which exceeds its goal of 2 before its cooling system ceased operation. And with that, the high-frequency instrumentation, which was the real new thing that Planck was adding, ceased operation as well.
Sorry, Chris.
Yeah.
How large is the Lagrangian point L2 in real sense? How accurate, therefore, should one be to land on that point?
Accurate should be one. I don't know that
If
question.
you're off by a little bit, then you're...
It's kind of orbiting it, actually. But they do have to make periodic adjustments to its orbit to keep it in place. I do know that much. Okay, so Planck, of course, is the third generation, so it's got to do better. And it has 3 times the angular resolution of W map. So basically, in a map, the Planck maps have many more pixels, and it has 10 times the temperature sensitivity. So the measurements that it actually makes are going to be much more accurate. So here you can see a comparison between the two. This is just a little cutout of the CMB sky map. With COBE, it's almost uniform. With W map, a little blurry, but you see it. Planck is very crystal clear. Put it in another way. We have here some maps of the Earth that have also been projected in the same manner that the CMB maps. And they both have the same resolution, so you see with COBE you can hardly make out the continents. With W map it's a little blurry, and Planck very clear. So this is the big thing that Planck has been trying to measure. This is the temperature anisotropy as measured by Planck. So with this, by itself, this map doesn't actually say too much. It might just look like a Jackson Pollock painting. To actually turn it into useful information, we need to know how the magnitude of fluctuations varies as a function of their angular extent over the sky. This quantity that we're trying to measure is called the CMB anisotropy power spectrum.
Where is the pole?
Huh?
Where are the 2 poles of the orbit?
I'm sorry, what?
Where are the 2 poles of the orbit?
2 poles?
Because there the sensitivity is very high. Because it has a lot of time observing these 2 spots.
Right. They would be, this is in galactic coordinates.
Right.
So yeah, the galaxy would be like there. The poles are on these quadrants down here, I believe. So somewhere around there.
So would these two spots have a higher sensitivity than?
They would have a better the noise at those pixels would be less. Yes.
Right, but would it show any significant difference from the rest?
I'm sorry, I'm not going to actually touch that subject, but all I can say is, yeah, you're right. I mean, the determination of the CMB would be more accurate there. How that actually affects our determination isn't going to be great, though. Okay. Actually, the slide looks okay. Okay, so this is the So the anisotropy power spectrum. Now, before I talk about that, I just want to point out that the temperature anisotropy can be decomposed into a linear combination of spherical harmonic functions with some coefficients that we call AL of n. And the multipole corresponds to an angular scale of about 180 degrees over L. So as we increase L, the angular scale decreases. So here I have some sample plots of this would be L equals 2, right? And this would be M equals 0, M equals -1, M equals 1. The M basically gives you the same resolution, but it just gives you the maximum and minima at different points. As I go to L equals 2, right, we get more bumps. The fluctuations are becoming smaller. And finally, we also have more possible directions that we can place them in. And we go to L equals 3, we get even further. So each ALM, we assume from the outset to be sampled from a Gaussian distribution. Now, of course, considering a non-Gaussian distribution for the ALM is also another consideration. I'll get back to that later. But for now, just assume a Gaussian distribution. And its average is 0, since we assume that the anisotropy is, the average, of course, should just be a uniform field. And the variance of it is given by this. Now, for different L and different M will be decorrelated from one another. That's why you see the delta function there. And the variance of it only depends on L, not M. Now, this C is the desired CMB anisotropy spectrum, and it represents the magnitude of CMB fluctuations as a function of their angular scale across the sky. Now, CL is a statistical quantity, and thus we, in principle, have to get several measurements of a particular ALM in order to calculate a sample variance and get the CLs. Unfortunately, though, we only have one universe from which to draw samples. This is not like, say, particle physics, where we can just keep running the collider, for longer to generate more statistics. We only got one universe, and we got to be happy with that. Fortunately, however, for each given L, the ALMs have the same variance no matter what the value of M. So we can use for a given L, we can use the different M value ALMs to estimate what the variance must be. In this case, the CLs. However, we're constrained because the number of ALMs for a given L goes like 2 times L plus 1. So therefore, the error on the estimate is going to scale like 1 over the square root of 2L plus 1. So this represents a fundamental limit on how accurately we can actually determine the CLs. Now, this error is not so important when we go up to very large L, where we have very many ALMs to sample. But at very low L, where we only have 5 or 7 or so forth, that actually becomes a serious constraint. And it's this sample error, this fundamental sample error, its limitation is what's known as cosmic variance. So this is the CMB spectrum as measured by Planck. Now, again, you can see right here the manifestation of cosmic variance. Here at low multiples, we have very large error bars, and those have not changed much from WMAP. WMAP already did a very good job of determining those. However, Planck has now done a much better job of determining the very small scale CMB anisotropy. To put it in perspective, WMAP started to become noise dominated around the third acoustic peak. Around here is where you saw the error bars get very, very large. Here we've almost tripled that. That's due to the triple resolution that Planck has. Right, so the green line that goes through it here, that represents the best fit possible with the simplest lambda CDM cosmology that we have. The lambda CDM cosmology is going to depend on cosmological parameters. So this is how we can determine cosmology from this picture.
How many parameters are there in this model?
6. Well, I'll get into that. Okay. So, I'm sorry, the slides actually got mixed up. Okay, so, all right, so where do the anisotropies come from? Well, initially, spatial variations in the energy density of the universe are called inhomogeneities, and denser regions with higher energy density, on average, are going to be hotter. Those are sparse regions are going to be cooler. And the CMB temperature anisotropies are created by inhomogeneities in the energy density. So imagine now we can decompose the density inhomogeneity into a sum of plane waves that evolve independently of one another. Now, because of the competition between gravity, which tends to want to further clump matter together, and the pressure in the baryon photon plasma, which tends to want to expand things, each mode is going to oscillate with a frequency given by Cs times its wave number k, where Cs is the sound speed in the photon baryon plasma. Now, the gravitational perturbations act as a forcing term. So inhomogeneities follow a kind of forced harmonic oscillator equation. So very roughly speaking, we have the density contrast here, and this is its equation of motion as a function of time. This forcing term depends on the gravitational potential. So what we get is something that's going to oscillate and have this sort of forcing term here. Now, early on, electrons and ions are too hot to form atoms. So photons are going to scatter frequently. They're not going to get very far without scattering and changing their wavelength and messing everything up. It's only later that when the universe cools down enough so that neutral atoms can form, photons are now able to free stream. They can travel freely without scattering. And this epoch is known as recombination. Although that's a bit of a misnomer because, in principle, the electrons had never been combined in the first place. But we're stuck with that. So the CMB photons that we see today originated from this era. And their point of origin defines a sort of imaginary spherical surface called the last scattering surface. Now, modes, okay, these delta K, those modes that were at their extrema, either at their peaks or at their troughs, at recombination, those are going to appear as peaks in the CMB anisotropy. Modes that are close to the origin, this sort of due to the forcing term, those are going to appear as minimum. And these are the acoustic peaks that we see in the CMB. And those are a powerful confirmation of the standard cosmological model that we have. So roughly speaking, if we have an inhomogeneity at scale k, this is going to correspond to an anisotropy at L approximately equal to k times eta 0, where eta is the conformal distance to the last scattering surface. So that explains the acoustic peaks, but it's not the entire picture, because recombination does not happen instantaneously. It is a gradual process, perhaps instantaneous on cosmological scales, but there is a finite time over which this occurs. And inhomogeneities with wavelengths smaller than the mean free path during recombination get exponentially dampened. That's because photons are allowed to go just a distance to sort of get themselves into some kind of equilibrium before recombination is finished. And this creates diffusive dampening in the CMB and anisotropy at small scales. This is a dampening tail. So these are the acoustic peaks, and out here we get the dampening tail. So this is a little picture I found. I think it was Wayne Yu of the University of Chicago. So what happens here? So let's just wait for the video to go through. All right, so here we're oscillating. Okay, we're just looking at a single wave mode here. So we're free to oscillate. The red is hot, blue is cold. Now suddenly we've recombined. Now the photons are free to move. All right, and this surface here is the last scattering surface. So an observer here is going to notice cold and hot regions in that last scattering surface due to that initial inhomogeneity. So how is this actually, so how do the cosmological parameters affect this? Well, for one, the Hubble parameter controls the expansion rate of the universe. So as H0 increases, the freeze out is going to occur earlier, and that's going to decrease the conformal distance to the last scattering surface. So since we have this relationship here, that means that anisotropies are going to push down, while the frequency will remain relatively intact. Now we also have the dependence on the cold dark matter density. And cold dark matter makes the matter photon plasma heavier. And this makes it harder for oscillations to occur. So this is going to suppress acoustic peaks at large scales. Not so much small scales, because when these guys are in play, when they've re-entered the horizon, radiation is dominating the universe, and so they're less affected by CDM. Now, the baryon density is going to affect things different. Now, both are forms of matter, both have a scale, both, in a matter-dominated universe, scale like 1/8 of the third, but they affect the CMB differently. Baryons, because they interact with themselves, they can support a pressure, and therefore they determine the sound speed. The CDM doesn't. So this increases the value, so by adding more baryons, we decrease the sound speed. And this increased the value of the origin around which inhomogeneities oscillate. This term right here. So by decreasing that, we increase that. So this means that peaks that are at their maximum are actually going to be heightened, while peaks at the minimum, or peaks that correspond to places where the inhomogeneities are at a minimum, are going to be suppressed. So we see the odd peaks here, they actually increase. Even peaks get decreased. So especially this and the cold dark matter density, how they affect the CMB is important to point out, because the CMB sees these two components of matter very differently. So we can make determinations of the relative contributions of those two. So now, how do we actually go about getting parameters from this? Well, in parameter estimation, it's the likelihood that takes the center stage. And sampling it can give us estimates on the parameter values and their errors. So for the CMB likelihood, we have an anisotropy signal, right, we call S. This is a vector over the pixel space. And we have the detector noise N. These follow a multivariate Gaussian distribution. All right? And the covariance of this distribution, the signal covariance, noise covariance, signal covariance depends on the CLs, that we give it. All right? So we put in a prediction for the CLs. We generate some CLs from our theory. All right, and then we get a value for the likelihood. And to find the best fit, we got to find a set of CLs which maximize L. So this is just a sort of cartoon version of what the CMB likelihood is. Planck has also supplemented this with other data sets, with the WMAP-9 polarization data, the Atacama Cosmology Telescope and the South Pole Telescope, which you know by high L. These are other CMB, ground-based CMB experiments. They measure a smaller region of the sky, but they measure it to much higher L. In the case of ACT, it goes to L to 10,000. And baryon acoustic oscillations, or BAO, independent measurements of the Hubble parameter. So these would be using cosmic ladder, or determinations of the distance and finding the redshift relation. And type 1A supernova surveys. Now the standard model of cosmology, which we call lambda CDM, has 6 parameters. So first is the Hubble parameter, the CDM, and baryon density. I talked about those. There's also the optical depth at reionization. And what that is reionization is once the first stars ignite, they tend to release more photons, which tends to suppress some of the small scale anisotropy. So we need to include that parameter because we don't know exactly the detail of reionization. And lastly, there are 2 parameters here, AS and NS. And these, I'll talk about them a little bit more later. Suffice it to say, they parameterize sort of the initial inhomogeneity that's seeds the CMB. Now, this is the minimal model, right, from which we can make several extensions to, and we can see whether or not those extensions do a better job of fitting the data. Several of them have been considered, and I'll talk about some. Okay, so now these are some of the highlights from the CMB, the Planck CMB results. So first off, it says about what the composition of our universe is. So 4.9% is normal matter, or just baryons. Also includes leptons, but you know, cosmologists don't care. We just call them 26.8% is cold dark matter, and 68.3 is that mysterious stuff called dark energy. Now compare that to WMAP-9 results. We find that for baryons and CDM, the Planck results are higher by 9, and in the case of CDM, a whopping 18%. While the dark energy is actually lower by 6. So you can see them on here. So we got some pretty significant differences from WMAP. That might have something to do with the fact that the Hubble constant that we have determined is significantly lower than what direct methods suggest. and also lower than W. Also, we determined that the geometry of space-time is flat to within a precision of 1%, which goes a long way to confirming inflation, which I'll talk about in a little bit. And the data are consistent with 3 flavors of neutrinos. So, first thing we should discuss is this Hubble discrepancy here. So in this plot, we have some of the various measurements of the Hubble parameter for different, using different methods. So the first 2 at the top, those are the CMB determinations of the Hubble parameter. So you can see that they are within, that Planck and WMAP are within their respective error bars. Planck's done a much better job. In fact, it's done a much better job than all of these other methods. And you would think that now that we've shrunk the error bar, we would probably be going more to the right. However, that is not the case. We're going more to the left. We're getting further away from all these other guys. So these other 3 here, these use local distance measurements. They use sort of the cosmic distance ladder to measure the distance out to some object, calculate the redshift, get that. These last 3 use basically geometric methods to directly calculate the distance to certain objects, the error bars. Now, what does this mean? Well, I wish I could tell you. We have to keep in mind, though, that each of the methods for determining these has its own weakness. In the case of using the CMB, we have to keep in mind that the result depends on what cosmology model that we have assumed. You know, if perhaps maybe we missed some kind of key component or key era in the cosmological history, this might change things. The weakness with the purple measurements here is they depend on standard candles, which might not always be so standard. And the last 3 here, they have problems. They're not very accurate methods of determining it, and they also depend weakly on the assumed background cosmology. So these probably, or this one especially, if that were the case, probably wouldn't be the most exciting thing. I think what would be really exciting is if the reason that they're so off is because the model of cosmology that we have is not yet accurate enough, or not yet comprehensive enough to make predictions. So now we can consider an extension to our lambda CDM model. Now, dark energy, the equation of state is always assumed to be -1, and that's the characteristic equation of state for dark energy. But we could, of course, make that a free parameter, and that's going to affect the expansion rate. Now, the data in Planck, at least at first glance, would seem to favor an equation of state less than -1. Now, from a theoretical perspective, this is very odd, because with that kind of equation of state, you get this sort of big rip cosmology, where the universe just flies apart, or you get a singularity at late times. However, I should very much warn you that the significance of this result depends on what other data sets are included. So if we include BAO and union 2.1 measurements, we get an equation of state. These are, the errors you see here are about 2 sigma. The equation of state is actually pretty well consistent with vacuum energy, although, as you can see, it is on the lower end. However, for the SNLS and independent measures of the Hubble parameter, they're actually pretty significantly off, especially when you include the independent Hubble measurements. We're, beyond 2 sigma. I would say, however, that this probably, the this result especially is probably much more a reflection of the fact that the independent measurements of the Hubble parameter are very different from what Planck prefers. So once you add in this data set, it's going to want to shift W up, which is going to need a compensating change in W in order to make things work. So I would say if you are working on phantom energy, I wouldn't put all your hope on this. Now we can consider, of course, a more realistic model of dark energy, which has a time-varying equation state. And the general parameterization that was used is this sort of linear parameterization with A, where A is the scale factor. The combined constraints from Planck, W map polarization, GAO, seems to give W0 well in line with dark energy. So I think it's safe to say that we are consistent with vacuum energy. So we can also consider now putting in some neutrinos into the mix. From the combined ACT and SDP data sets, this is what we get for the effective number of neutrinos. Now the standard model value would be about 3.06. And these are the 2 sigma errors. So we are within 1 sigma. You're well within 1 sigma of the standard cosmological result, although perhaps maybe a bit on the high end. In addition, neutrino masses, by including them, this is going to have the effect of suppressing small scale structure. So that, of course, so neutrino masses can also be constrained using CMB data. And Planck has improved the constraint. The original, I think, was about 1.5 eV, something like that from WMAP. We've now put that in half. Oddly enough, just about no difference in the Hubble parameter doesn't really change much in that case either. All right, now this is probably one of the big anomalies that everybody's been talking about, and this is the large small-scale tension. So we see that between large and small scales, larger angular scales tend to favor a lower anisotropy than smaller scales would suggest. So if we go back to this picture here, so as you can see, the fit is pretty good at large scales, and because we have so many more data points out here, the best fit, the green line, is mostly determined by them. If we use this best fit and we go back here, we see that a lot of the data points are, almost all of them are on the low side. You would expect from random noise that you would have them kind of evenly spread sort of across there. Now, the chance of that happening, the significance of that, it ranges from 2.5 sigma to 3 sigma, depending on how you separate out the components, component separation that you use. Either way, that's a pretty high significance. Maybe it's not the 5 sigma that particle physicists would like, but we're cosmologists, we'll take a 3 sigma. Now, the WMAP 9 also shows this high low-L tension, although the significance is only about 1.8 sigma. Now, I believe the reason may be because we've now have many more higher multiples. The fit is now much more biased for high multiples than it is for low multiples. So it's kind of moving it up. Now, you can see kind of the result here. Now, to test just what effect this has on the other cosmological parameters, we can try an extended model from the basic 6-parameter lambda CDM, and now include this sort of low or large scale scaling, A low, such that for L greater than or equal to 50, CL is the usual lambda CDM. And for L less than 49, it's CL is equal to A low times the lambda CDM prediction. So we allow the low scale anisotropy to go freely as it pleases. Now you might think that, well, we've got all these other problems. You know, we got this problem with the Hubble parameter and the dark matter, or CDM and baryon density. Maybe that will change things. And it turns out not really. Let's see now. So we would think, so here are the histograms of H0. The default model is red. That's lambda CDM. H actually goes a little bit lower, if anything. So it's these large-scale tension and the Hubble discrepancy are probably not related to one another. Okay, so what am I doing on time? We got
5 more minutes.
Oh, okay. All right. So, well, inflation. Huh? All right. So, inflation is the most popular explanation of the CMB uniformity. Now, as I said, it's an incredible level of uniformity. Now, you wouldn't expect that from the standard Big Bang model because a lot of the regions of space, any distantly separated region of space that we see today on the sky was always causally disconnected, and they were never in contact. So how do you get this level of uniformity? Well, inflation proposes that in the very early universe, you had this period, very brief, very rapid expansion. Now, that changes things because before inflation, you could have these regions in causal contact with one another, they get into equilibrium, and then inflation rapidly separates them, giving the appearance that they were never in causal contact. Now, that's a very nice way to solve that. It also solves some other problems. It explains why we have such a flat geometry. You would expect that if you had even just a little bit of curvature in the early universe, it would come to dominate. So it had to start at an extremely flat geometry to get what we see. And it also explains why there are no, or at least very few, that we haven't seen yet, topological defects, monopoles, domain walls, or cosmic strings. In fact, inflation was originally proposed to solve this problem, but you get all those other things. Now, those are just, at best, post-dictions. They're not predictions. They're just there to kind of, get a problem out of the way. In order to be, a compelling theory, it's got to make some predictions, and it does. So, what it gives us is inflation explains that initial inhomogeneity. It gave us that seed that became the anisotropy. So I won't, since I'm running out of time, I won't get into that. Now with inflationary, this is probably the biggest plot in the inflation results in paper, for good reason. The curves here, the shaded regions here, show the 68 and 95% confidence, the kind of 1 sigma, 2 sigma regions. Now, inflation models will make predictions for the primordial tilt of the spectrum. That's, I should point out that most inflation models predict this kind of primordial power spectrum that gives us the anisotropy. And it's parameterized by AS and NS. And there's also another quantity called R, which measures the contribution of gravitational waves to the anisotropy. Now, AS is very well determined. NS, pretty well known. R, completely unknown. So if we look at the plot of, so each inflation model is going to make a prediction for R and NS. And if we plot it on here, let's say for, well, this is the most popular one, phi squared, all right? This line segment here are the possible NS and R values you can get from that model. And if the model in question isn't at least within the light shaded region, the 95, then your model is pretty much discounted. It's not going to work. Now, a lot of the very simplest models are actually in some pretty serious trouble. So probably the simplest one was phi squared. This was probably the first, at least theoretically successful model. It's now in some trouble. The most successful model is this one right down here, the so-called R squared, which is so-called because it originates from a higher order terms in gravity. So inflationary constraints say that, first off, the Harrison-Zeldovich spectrum has been ruled out at greater than 5 sigma. Harrison-Zeldovich would be this point down here, and S equal to 1 and R equal to 0. Now, you can actually get almost as good a fit by assuming an S equal to 1, by allowing the helium abundance and the effective number of neutrinos to vary. However, the helium abundance you get is incompatible with BBN, and a fourth neutrino family is required, although maybe that's not such a bad thing for some people. Huh? This one?
So yes. So how about phi to the 2/3?
Phi to the 2/3. Yeah, this would be the one in red here. So we're within the 95% at least.
Excluded or?
It's not totally excluded. I would say it's in trouble.
How about linear in phi?
Linear in phi, right on this line here. It's the yellow. So the upshot is actually that models that have a convex potential, that kind of are convex up, that can hold water, are disfavored over concave models, one that kind of curve down. That seems to be the thing to take away from here. Now this is the estimate on the spectral index here. We've got it to a really great precision. The Planck plus WMAP polarization constraint on R is now almost at 0.1 for 95% confidence. This is much better than what WMAP 9 has been able to do, so by a factor of 4, but only slightly better when you take in STP. Now these results are robust to external data sets, meaning that if I add in some other data sets, I'm not going to change these results by much, which signifies that Planck is what's giving us the greatest constraints on these parameters right now. One interesting thing to note is that the running of the spectral index, as measured by Planck, gives it marginal detection. It's negative at the 1.5 sigma level, marginal, but I think interesting. This is somewhat interesting because a lot of the simplest models of inflation actually give you a lower running by a factor of magnitude. So I think this is further evidence that simple models are kind of on the way out. So, okay, I've touched on these. So this is my contribution to the Planck team. So I'd like to take at least one moment to point it out. Now, in the previous, we've assumed that the form of the primordial power spectrum is this simple power law form, but that's very restrictive. And while it may be true for most inflation models, there could be some more exotic alternatives that give you features in the spectrum. So if we allow for this for a more general primordial power spectrum, we can try to reconstruct this f of k, this feature that modulates the featureless spectrum. And what we found is actually there seems to be a modest detection at small scales. So in some cases, almost a 3 sigma detection. So, this is of course something I'm going to be following up on. So, to be continued. So, I think I'll probably finish up in this case. Right. So, in case some of you were wondering though about non-Gaussianity, I said before that the ALMs were assumed to be to be Gaussian, but of course we could consider an extension of that. We consider maybe the 3-point function, which for a Gaussian field would vanish. This might actually have a non-vanishing contribution. In all cases, though, in all possible shapes, the detection is the non-detection. It's consistent with there being no Gaussianity. So, to conclude, so Planck has shown that there is good general agreement with lambda CDM. We can see, from the anisotropy spectrum, the best fit looks very nice. But, there are some anomalies there, some hope for something new. The Hubble parameter is much lower than other measurements suggest. This means that you can be sure that Planck and a lot of other experiments are going to be checking their results much more closely in the future to try and make sure this isn't some systematic effect. And if nothing is wrong with these measurements, then it might require a rethinking of standard cosmology. So Planck has shown that there's an anomalously low anisotropy at large scales. This seems to be unrelated to the Hubble discrepancy. The question is of course, where is this coming from? Is this a source from a primordial source, from say inflation that suppresses scales, large scales at early times? Or maybe is this some kind of late time effect that might be giving power to small scales later? I don't know. A lot of inflation models are now being ruled out, or at least are in danger of being ruled out. The simplest models seem to be almost out the door. Unfortunately, as many had hoped, however, evidence for primordial gravitational waves, non-Gaussianity, or isocurvature, which I apologize I didn't get to. Unfortunately, there's no indication yet of these. Although I must say, the polarization data from Planck has not yet been released. That is still being cleaned and perfected. Hopefully, when those results are released, we can maybe say a little bit more about gravitational waves. Thank you for coming and for giving me the opportunity to talk.
Thank you for the very interesting talk. We can, why don't we get the panel members to come to the front, then we can take some questions to Chris and all the panel members.
Okay, Chris.
Chris. There's a microphone over there. There's a microphone. 有线的。Okay, first, let's take some questions to Chris.
here to have a discussion.
Okay.
Is questions only from panels or
Yeah,
everybody?
yeah, everybody.
Oh, all right.
Can I begin?
Yeah.
First, I think this is a good talk. And I would like to, although I sort of gradually understand your theorists, your types, and experimentalists, but nevertheless, because you are in Planck team, so probably.
In between.
Oh, okay, that's good. Now, the POMA cluster has a size of maybe a few degrees, and it has this ST, Sunyaev zero-Vector effect. But when you map the whole sky, did you sort of get rid of the POMA cluster that will contaminate your data?
Well, you are talking about component separation, and then I'm afraid I'm maybe not too keen on that. The SC effect is included, at least parametrically. We include perhaps at least some basic models, and which depend on some nuisance parameters that are then marginalized out. So this accounts, so the likelihood that you see accounts for that stuff.
But those SC effect was taken from SPT?
I don't know off the top of my head how the model, or where the models actually came from.
Okay, thanks.
We have questions from the audience? Yes.
I'm just curious how the Planck is doing better than the previous experiment. It's like WMAP. Do you have any, for example, zoom up, the graph in the high multiple, for example, compare the experiment?
Well, I did have a picture, of how, in terms of the map resolution, how those look.
Yes. But,
yeah.
I'd like to see it in the, for example, multiple, the high
Yeah.
multiple structure, how the fitting can be improved in the high multiple area. So, the long time ago I asked you, so, for example, such a fitting can affect the low multiple as well. But I like to have some kind of the visualized, the fitting result.
Mm-hmm.
Do you have any backup slide?
No,
No.
none of that. I mean, as far as WMAP is concerned, it's it's an improvement of a factor of 3 now. So the high multipoles are now giving a lot more weight to the data, which I think might be in some sense biasing the fit, giving preference to fitting the high multipoles while leaving the low multipoles out in the cold. That's what probably is giving you this larger discrepancy over WMAP. Fortunately, I don't have the kind of picture that you would like.
I'm a little confused by your question though. If since Planck is 10 times better in resolution, so in principle it's more the information, the error bars for higher modes should be less. So
for example, this one is all the zoom out images. So I like to have the detailed structures, how the
but that was a spherical harmonic analysis, right? So everything is already there, it's all overlaid. But if you have in principle a higher resolution, say 10 times better,
3 times. The
3
resolution.
times,
Yeah.
Angular resolution 3 times.
Angular resolution
Right.
is 3 times.
Right.
And the noise sensitivity, or I guess the temperature sensitivity, is increased by a factor of 10. So the resolution allows you to go up higher, the multiple, and the temperature sensitivity is what decreases the error bars. Roughly speaking, there is some,
Okay. Now, so therefore, if you get you have a 3 times better in angular resolution, do you correspondingly are you able to go 3 times higher into L?
Yeah, just about.
Which happened to me. It's not always me.
Yeah.
Higher is better design this way. Always.
I mean, in the map that, or in the picture I showed of the temperature and anisotropy, it cut off at 2500. Although the actual measurements go up to over 3000. It's just that beyond 2500, the error bars start to get progressively larger, and that's because the noise in your detector is starting to become significant and the resolution is starting to degrade. In WMAP, you know, you get noise dominated around, I don't know, 8,000 or something like that. So yeah, roughly about 3 times.
Yes.
So it seems that the Planck data, in the Planck data, the number of neutrino species can be constrained. So if I remember correctly, it's like 3.36 or something. So why don't people just use integer to feed the data? You know, currently you are using some fractions. Why don't people just use integer?
This is due to the fact that neutrinos actually decouple earlier in the universe than the rest of matter, and during that time, some energy is actually deposited into the photons, but not the neutrinos because they have decoupled through the annihilation of electrons and positrons. So, assuming we actually have this background of E minus E plus pairs that's around here. Neutrinos decouple, they can't receive any energy from them. So those annihilate, they give off their energy, and so they have a different temperature. And you can sort of account for that temperature difference in the effective number, which gets slightly changed.
That's an effective. It was not the actual integer counting of number of flavors.
Right, right.
I would like to know the panel members' reaction to the Planck result. So who wants to go first?
Relieved?
Or?
Well, as a string theorist, you personally think a single field inflation is pretty contrived. So they tend to be a lot more scalars coming from a string-inspired model. So not seeing non-Gaussianity is slightly disappointing. But also, it's kind of interesting now the phi square term is being rolled out. That's certainly most vanilla type. And the natural question to be asked is that, okay, so as Chris was pointed out, that they are those concave model, or in other words, if you treat it as a polynomial type of potential, then you're looking at the low powers, right? So then the natural question will be asking, well, so how do you prevent all the radiative corrections from all the well, generally they will generate all the higher power terms as well. So to a string theorist, I think that's a good news because at least you can try to ask whether they are, for example, additional symmetries or additional way to account for why, for example, the correction are actually not there. Right? For example, the phi to the 2/3 potential, that's actually come from those monodromy type of inflation that Iver Silverstein and company was coming up. So that's good news. But then the relatively bad news is that, well, so then you also are seeing a very small r, then that means the inflationary scale is kind of low. So, and we are having a kind of funny, it's kind of quite far away from a typical string scale. So we are kind of halfway in between.
We're still, I mean, I guess we're at the gut scale, pretty much.
Yeah, okay, we're still at gut scale, so that's probably still okay. So, but like you said, there's only, you're scanning a few of simplest example over there, so there could be other things as well. So, yeah, I don't know.
I mean the models also seem to favor, I guess, small field models, where you're not, in the large field models, you're talking about transplanking values.
Right, which generally will generate large R.
Yeah, yeah.
Right, so that's basically
Yeah.
fine.
So I don't know. It seems maybe it's moving away from the place where
But small field model then now basically tells you, well, you would need to fix the initial condition somehow. Otherwise, you have overshooting problem. Right? If you your field start rolling too fast in your potential, then you kind of just go over it. You don't generate enough number of etons. So then that shifts the problem to a different.
Sure. I think on initial condition, maybe, I don't know, Pison, you might have something to say about that.
Right. I feel very pretty excited with this new Planck data. It poses a lot of new both confirmation as well as challenges to both cosmologists and hopefully also string theorists, etc., particle physicists. A lot for the looking into, including this, as what Chris has emphasized, these apparent lower than average lower mode behavior, whether that is a advertisement of something happening before inflation, having to do with the initial conditions or whatever, and that I feel that's one thing rather interesting. There are a couple more things that Chris didn't mention today, but it was with Planck was this cold spot, etc. Right? Yeah. Now back to the inflation issue, and I just like to add a couple more comments. It's also meant to be somewhat provocative. Chris, you noticed that perhaps the next day, second day, or whatever day, Paul Steinhardt posted a paper and got all excited that this new Planck data is indicative that the conventional wisdom about inflation is having a problem, and I believe there was this UC Davis meeting just not too long ago, and Steinhardt was there too. Yeah.
You're not referring to the one on the 20th, are you?
Haven't
think it's happened yet.
All right.
Okay.
Yeah. So this last part was meant to be a question instead of a comment. Have you read the paper, and if so, what's your comment on?
Not exhaustively, I'm afraid. I mean, it's a good news, bad news situation. I mean, actually, I would say it's good news. We're really putting a lot of models on the chopping block now. But I mean, at least we do have some models, such as sort of R squared, and also the sort of Higgs inflation too, which are almost equivalent, really, in terms of their Lagrangian. They seem to
yes.
be, huh?
Yes.
Yeah.
By some transformations, you can cast it into an R squared.
Exactly. So I mean, I think that at least shows that and those models are right in the 68%. So those, I mean, it would take an incredible improvement in accuracy to try and kill those, or a big surprise. So I don't know, Steinhardt, he was the, I guess, cryptic or epcorotic,
Epcorotic or cyclic.
Non-Gaussian prediction can make epcorotic
Yeah.
high, and it's pretty much going through zero right now. So I don't think it's offering anything.
Yeah. Okay.
But I believe lately he's given up that name and more like just calling it cyclic models.
Well, whichever names. I mean, the point is not what's the. I mean, also, what does it mean by against the conventional wisdom about inflation? I mean, how does it quantify? I mean, it's trying to talk about there's a different potentials that inflationary can adopt it. But the thing is that if you want to say something is fine-tuned or not, you have to be able to have a mechanism, put a measure on this parameter space, which he hasn't been able to. So I think, I mean, it's a paper with a strong agenda behind.
But I think they
more
try to put connect this inflation scalar field with the Higgs field. That's a little bit contriving, is it?
Yes, it's a very contriving. It's all right because the scale is just not there.
That's what it meant. I mean, you have to fix the potential here with this scale and the other potential there with the other scale. And I just don't think that that paper is worth seriously how do I say interpreted.
But
well, I mean, the fact is, on the same day there was another paper by Steinhardt and for his former postdoc is talking about basically it was not coincidental like two papers appear on the same day. The other one is appearing, talking about the equality prediction. But I don't think. Yeah, I mean it's well known he's not liking inflation, so I mean he's not going to change his stance after Planck data coming out.
So what model is that? Two sheets collide. That's what you mean.
Right. So it's like and they have an internal inflation situation.
Question?
well, I was just going to say, I mean, at least on the, if we were to just treat the potential, as just some kind of, phenomenological model, at least we've found something that is very well consistent with results. Now, I guess maybe the challenge should be to try and find maybe a better theoretical motivation for introducing it.
First, I need to say this is a very interesting talk, but I need to say sorry because I'm not so excited for the release of the. Yeah, I have been looking at the CMB data for a long time, and every time you see the parameter shift again, like the Hubble constant from 70 to 68 now. So I'm really, but something interesting in Planck, I think is first is like this inflation is well discussed, and another interesting thing I'm waiting is for this low quadruple. If I remember correctly, this a quadruple just getting inside the 1 sigma. This is 1 sigma or 2 sigma.
Yeah, it's just I think at the 1 sigma.
It's 1 sigma. So
yeah.
Any people interested in this issue after Planck released data?
Well, if you I think what's more interesting is to look at it within the context of this larger low L suppression. If you find just one, say you have, a few thousand error bars or a few thousand data points with error bars, and you find that they're all pretty well within 1 sigma, then you find one that's within 2 sigma. Well, maybe, or let's say 3. Well, that might sound pretty exciting, but you have to keep in mind you have 1,000 points from which to draw from, essentially, assuming that they're independent, that their points aren't correlated. It's not any surprise that you would find at least one, that's outside of 3 sigma. But if you find several points that are consistently below, the predicted value, well, taken together, that actually increases the significance of that result. So, I think just focusing on the quadruple, I think it should be looked at in a larger context of the total low L suppression.
What if the Milky Way is located in a very strange place, where you have it's in sort of supercluster. It's in
I'm sorry, could you?
Milky Way galaxy is not in it is in a unique place where it's surrounded by some sort of supercluster, these kind of things. And would it affect the low L or not?
If we're located in what cluster?
Supercluster.
Supercluster.
He's referring to
Yeah.
local effects.
Yeah.
Local
yeah,
effect,
yeah.
because you have only one spot of measurement. And if this spot is in a very strange spot, then you will see all these strange feature in the low L. In high L, you wouldn't.
Right, of course. No, that's interesting. I think it's something to consider. You know, if it's a more local effect, it's going to affect more of the sky and hence, you know, lower L. I guess probably wouldn't it mean though that we're sort of in an underdense region? Overdense.
We just need some large scale fluctuations around us.
Okay.
Let me ask you a question. Can Planck be the machine that eventually allows Alan Guth and Lindy Solar go to Stockholm?
He asked me to think about this, and I'm probably gonna have to say, at least for the foreseeable future, probably within his lifetime, no.
Okay.
The reason is because the effects of inflation that we see are very indirect, and in order to really and we rely on basically just one universe. As I said before, we're limited because of cosmic variance of really refining this picture. It's it's conceivable that you could, it makes I think some successful predictions. Some, at least with one model that's very close to the preferred value of NS and R. But there's no reason to say that perhaps we could have other models that come out that don't rely on inflation that somebody hasn't thought of yet that gives us an SNR that's consistent. I think the only way that, unfortunately, actually trying to find an inflaton field, that does everything, well, the scale of inflation goes up to the gut scale, and we're nowhere near measuring anything on that scale directly. Yeah, tough, and of course the Nobel Prize Committee, they only like to give Nobel Prizes for things that have been rigorously confirmed, so unfortunately I don't think Guth and all of them are going to be getting a call from Copenhagen.
And do you think that a new machine that can actually send them to Stockholm? If there's one, what would the measurement be?
I sorry, I just don't think there is one. Not right now.
You want to say something?
Okay, just this is lighthearted comment. There's this number problem. I think just by counting fingers, it will be more than 3. Those who have made seminal contributions to this. Starobinsky, of course, was even before Guth and Andre Linde. And funny enough, or well, interesting enough, that his original R² model is actually currently in favor, right? So are we going to exclude him? And then there's also the famous antagonist Paul Steinhardt, who had, and as well as Albrecht, and Andy Albrecht, they have concurrently made the contribution with the new inflation. So just by counting numbers, you already got 5, 6. I don't know how many. And now that one of them is in the belief that this original thing that he had helped contributing has some inherent defect, and so I think his opinion will also be counted whether he needs to, he's he's qualified to share, or whether this notion is already concrete enough. But I'm taking a slightly different attitude from Chris in this count. I thought that in the case of this, it's perhaps not necessary that the specific model be proven correct, or whether that specific scalar field has been found, but rather that the notion that the universe has undergone a brief period of huge expansion, that concept, that idea, which in principle does explain a lot of what we have seen, that itself, I thought, is deserving pushing them over to Stockholm.
Other members want to say something regarding to this question? Do you have other questions from the audience?
The fact that you see this wiggle in the CME power spectrum, does it prove inflation?
I'm sorry, what do you mean by window?
Yeah, the wiggle things.
Oh, wiggles.
Does it necessarily imply inflation, or there could be some other mechanism producing?
Okay.
Of course, it rule out in the old days, inflation has a competition with the cosmic string, and so it rule out the cosmic string because cosmic string is incoherent sort of things, and inflation has a coherent oscillation. But would it really imply inflation?
So when you refer to the wiggles, are you referring to the acoustic peaks?
Huh?
Are you referring to the acoustic peaks in the?
Right. In the
that I would it definitely goes a long way to proving. Well, the wiggles themselves are more evidence of what comes later. Basically, these acoustic oscillations in the baryon photon plasma in the early universe. The initial perturbation or inhomogeneity that generates or seeds them, that comes from inflation, and what the models suggest is that, of course, it should be close to ns equals 1, although a little bit less.
Okay, and the power index equal to 1 is a prediction of inflation. But for this oscillation in the CME power spectrum, what you really need is something more general, right? As long as the initial perturbation, I mean, it's a general thing. I mean, because the perturbation is doesn't have any velocity when it is a super horizon, and when it enter horizon, it starts to oscillate, right? So this is very general things. Anything that has this feature without any initial velocity would do this oscillation in the power spectrum.
Right. Well, I mean, inflation is probably the most, probably at least the most consistent way of generating these initial conditions to get inflation. But as you said, I mean, there was cosmic strings is out, but that was at one point. At this point, no. I mean, it's the only game in town, really. And until somebody can think up of a better idea, I don't think inflation's going away. That's why I think that giving Alan Guth and Sterpinski or whoever the Nobel Prize for this is probably not going to happen, is because inflation is there mostly because it just does the better job, but maybe not but maybe not the best job.
Yeah, but this is a well-known thing in science and physics, that it's a paradigm game. So unless you have a better one that's convincing enough to take over its place, otherwise Thomas Kuhn is right. So currently we're under that paradigm. Now, just talking about the support for the notion of inflation, just following that discussion just now, I thought the salient feature wasn't quite NS equal to 1, which you can just hook it up as Harrison-Jodovich spectrum, etc., without any good physical motivation, but it is actually NS be slightly less than 1.
Yeah.
That was the persuasion.
Sorry, I should have mentioned that. Yeah. Right. And I mean, I think
any replacement of this paradigm will need to come up with something as predicative as that, because this was made 30 years ago, way before Kobe, before WMAP, of course not before Planck. So if you want to call that a prediction, it's not too far off.
No, it definitely is. I mean, inflation, when it was first proposed, it was just to sweep under the rug. You know, Alan Guth just wanted it to sweep monopoles under the rug. And we also it solved the flatness and horizon problem. It solved problems with the Big Bang Theory. If that's all it did, then it would just be, just a way of getting around some inconvenient truths. But because it makes this prediction about anisotropy, that's why we take it so seriously. And I mean, I think, a lot of people kind of coming down on inflation, but I think it's got some problems, but I think it's too good an idea to die. It should.
Actually, recently I have added one more credit to the inflation concept about the one remaining problem, quote unquote unsolved. That was the entropy problem. And it appears that inflation can itself solve the entropy problem as well.
Gauthier, you want to say something? Okay, in closing, let me ask the last question. So I want to reinforce Henry and Gauthier's comment that it looks like the lambda CDM works too well. So the analogy is that in high-energy physics, you have the so-called nightmare scenario where HC works too well that you got no guidance that leads you to point to a new direction where the new physics is. So my question is that whether we are facing another nightmare scenario with the Planck result.
Cosmology isn't particle physics. As I said, obviously. Cosmology, we're naturally limited. We can't just it's observational science. It's not experimental science. So we're limited by just what nature provides us. I think the greater problem is just, with the case of NS, or determining NS and R, are we really going to be able to increase the accuracy on that any more than we've got? Where do we go from there? The polarization data is going to be coming out. I think we're going to be able to make, probably in the future, there's going to be better determinations of polarization spectra. That's going to improve things, but I don't know, unless we actually make a positive detection of tensors or non-Gaussianity, I think it is going to be kind of limited. That being said, I think there might be something to these anisotropy, or the low large scale anisotropy. There might be something to the Hubble discrepancies. This might require maybe not a rethinking of sort of the large scale and the early time physics. We might have to bring things closer to home and think about what happened in the evolution of the universe. What might, what's happening maybe just being in our neighborhood of the woods. Are we in a unique place in the universe or not? I think there's some questions to go from on this. How much further we're going to be able to go? I don't know. I'm kind of
I have
Yeah.
a question. Does the Planck team has an internal discussion of next mission?
There is no.
Next mission.
Well, I mean, there's no like you know, it's not like the Planck team moves immediately to the next mission. It's more just various people from Planck will maybe go on to try something else. There's actually been an effort by people in Europe to get a new satellite mission called CORE off the ground. That would be they 2 years ago they were in competition, and I think they made it to the final 3 or 5, but unfortunately they were not picked up. But they're going to try again and try again.
What?
Huh?
To do what?
Hmm?
To do what?
Well, try and measure the CMB more accurately to try to, but especially concentrating on polarization.
Maybe you want to say something?
No, I too many junior people here to voice my opinion about the future. There's not much talk about the late time universe today, and I'd just like to add one more, if I may, about W's less than -1, or let me recast it, about whether the dark energy was responsible by a Planck cosmological constant or not. You have any comment on?
Like I said, everything in the talk. I think the results for W less than -1 are very iffy. I think it's more just a reflection of the fact that you have discrepancies with other parameters between data sets. If we had the same data, if we had different data sets giving us more or less the same significance and answer, I would say that there's something here, but that's not what we're seeing. Yeah.
Okay, I'm afraid we have to close this interesting discussion. All right, let's thank all the members and the speaker again. Thanks for coming. And for junior people, whoever tells you there's a nightmare scenario, don't trust him. Okay?